At 6:04 in the evening, the ground beneath northern Venezuela ruptured with a magnitude 7.2 earthquake. 38 seconds later, before people could understand what had happened, a second rupture struck nearby. This one reached magnitude 7.5. Two major earthquakes, less than a minute apart, hit a populated region between Venezuela's Caribbean coast and its inland cities. Buildings failed. Roads were buried or blocked. Communities were cut off by rockfall. By July 7th, authorities were reporting more than 3,500 deaths, and that number was still changing. The disaster was not simply one earthquake followed by a normal aftershock. The first event is now treated as a foreshock to the larger rupture. Together, they exposed why the mountains west of Caracas can turn shaking into several disasters at once. To understand what happened, begin with the clock. The United States Geological Survey places the first earthquake at 22:04:33 UTC on June 24th. Its magnitude was 7.2, with a reported depth of about 20 kilometers. The second began at 22:05:11. It was magnitude 7.5 and shallower, at about 10 kilometers. Its epicenter was roughly 28 kilometers southeast of Yumare. Magnitude is logarithmic. A 7.5 does not release only a little more energy than a 7.2. The difference is roughly a factor of 3 in energy, and because the larger rupture was shallow, more of that energy reached the surface without being weakened by a long journey through the crust. But the 38-second gap is the part that makes this sequence unusual and terrifying. Earthquakes change the stress around neighboring faults. When one section slips, it can unload stress in one direction and add it somewhere else. Sometimes that change helps push an adjacent section past its breaking point. Scientists need detailed fault models before they can say exactly how one rupture influenced another. The safe conclusion is narrower. Two distinct large events occurred close together in space and time, and the second became the main shock. The first did not warn people in any useful human sense. It became the opening movement of the same catastrophe. Northern Venezuela sits in a complicated boundary zone between the Caribbean and South American plates. Their motion is not absorbed by one clean fault. It is distributed across a network of strike slip and related structures running through mountains, valleys, and the coast. That geography matters because the shaking did not stop when the faults stopped moving. Steep slopes rise behind the coastal settlements of La Guaira and the roads west of Caracas. Strong shaking can loosen fractured rock and saturated soil. Gravity then continues the disaster through landslides, rockfall, and blocked drainage. USGS models initially warned that earthquake-triggered landslides could be widespread. Satellite assessment later suggested the overall landslide extent was lower than those first models predicted. That did not mean the danger was gone. Analysts still identified localized landslides along coastal roads west of Catia La Mar. Rockfall and large boulders obstructed transportation. Some inland communities may have been separated from the coast by partially or completely blocked routes. This is an important reversal. A model can correctly identify a serious hazard while still overestimating how much of the landscape failed. Rapid disaster science is not a finished verdict. It is a process of replacing the first probability map with observations as clouds clear and satellite images arrive. The same uncertainty applies to the human toll. Early casualty figures rose as rescuers reached damaged neighborhoods, and hospitals received more patients. 12 days after the earthquakes, Venezuelan authorities reported more than 3,500 deaths, over 16,000 injuries, and thousands of people without homes. Those figures describe a moment in an active emergency, not a final accounting. The medical consequences can also outlast the shaking. Interrupted water, crowded shelters, untreated wounds, damaged clinics, and blocked roads can turn a seismic disaster into a public health crisis. Then come the aftershocks. An aftershock does not need to match the main shock to be dangerous. A structure already cracked by the first two earthquakes may fail under much weaker shaking. Rain can remobilize loose slopes days or weeks later. A boulder that stopped above a road can move again. That is why official guidance after a sequence like this focuses on damaged buildings, steep slopes, unusual sounds, new ground cracks, changes in water flow, and local evacuation orders. The danger becomes smaller with time, but it does not vanish when the news cameras leave. There is also a deeper lesson in the 38 seconds between the two ruptures. We often imagine disasters as single moments. One fault breaks, one wave arrives, one city shakes. Venezuela's earthquake sequence shows how misleading that picture can be. The first rupture altered the physical system. The second released more energy. The mountains converted shaking into blocked roads. Damaged infrastructure converted isolation into medical risk. One event became a chain. Science can map that chain, estimate where slopes may fail, and update the picture from space. It cannot make the first numbers final or reduce thousands of lives to one magnitude. The earthquakes were separated by 38 seconds. Recovery will be measured in years. Share this with someone who follows earthquake science and subscribe for the hidden systems behind the events shaping our world.